Greetings, healthcare colleague. My name is Kevin Kotchik. I'm the founder CEO of Chemical Q Device here for this is discussion number 72, Thursday, March 2nd, 2023. Now, the big thing with all this is in order to get algorithms, they have to be programmed. In specific popular platforms, you'll download Anaconda and you'll get Python on Jupyter Notebook or Jupyter Lab. Now, how all this works is Jupyter Notebook, I'll go over a lot of this, is you'll have it in a web tab. So it's like that because it can get free updates. Now, to develop neural networks, I'll show you kind of how things are conventionally and then how things are, hybrid with quantum insertion with this. Now, the new insight with this is basically, I did a previous Prisma study and it was just 191 of these approvals that were most relevant to quantum. And now I'm further narrowing it down to reconstruction algorithms and segmentation as well. Now, with the notebook, you have this interactive environment. So you can write and run code with it. And you can access a Jupyter Notebook through, Anaconda. You could do it through Qiskit. And it's a helpful way of programming with languages such as Python. Now, there's other things tied to it, JavaScript, and you can do cell toolbars, default and slideshow mode. And in specific, you have a kernel. So the kernel runs the code, runs the user's code, and then you have 3 different front ends with this. So this is what a typical Jupyter Notebook looks like. I'm assuming this is opened up in Google Chrome. So you'll have a terminal console, a Qt console, and then a notebook as well. So the Jupyter Notebook. And again, you can upgrade to, or you could choose to use, Jupyter Lab. It's a little bit heavier, but it gives you other functionalities. So you also have these things called comms. So comms allow, front end and kernel talk. And then this is a tutorial. There's several Jupyter Notebook tutorials, but basically what to do when things go wrong, just getting up and going. If you want to get up and going, I suggest first doing Qiskit with OpenQASM. It's Open QASM. And then I would graduate to the Qiskit Jupyter Notebook because it already, has some things installed. And then I would graduate to the, the Anaconda, the Jupyter Notebook. But there's all these things. So verify you have the latest version, open the correct version. So do Jupyter-Notebook. Make sure, you're running the right kind of browser, basically. And then if you can't start a kernel, run this kernel spec. And the list goes on and on to specific issues with Windows. So this week there was a Siemens Healthcare. Actually, they call themselves the Healthineers, and in specific, it's using quantum annealing this Kubo, and then with Kubo on the way for a reconstruction algorithm. So they're using D-Waves hybrid solvers, and then there's different linear systems. So there's forward problem, and then you also have inverse problem. So inverse problem, Harold Hasidim Lloyd algorithm, COA, that's more for gate-based, and then you have matrix inversion for annealing. Now, this is one of the slides here. So basically, what you want to look at is the one from the transition from no noise to with noise, what images withheld the best. So if you look at this bottom row right here, you'll see for, so some of these, say, for instance, this second to last column loses fidelity with noise. So they're basically saying, using their quantum annealing approach, how is that holding up? And this is basically the data that they get. So, with noise, you're looking at the red triangles. So it tends to hold up better than something, than some of these other ones that get scattered, such as the green squares right there. Now, here's just a portion of the code. I don't think this is anywhere close to, what you would need to, use D-Wave, but you can contact D-Wave if you're interested in, basically a Kubo is a binary classification. So it's a step in the right direction of using more and more quantum. So this is an example of classical computing with it's Python running a Jupyter notebook. And this is for a convolutional neural net. So you'll get familiar with these terms. So you have terms such as, so they're packages and things you have to load in, TensorFlow, Keras, and then a lot of these things, such as like a pickle, it's many things combined. So when it says to import it, I created this little chart here on the right as far as, Keras is a neural network library, sequential arranges things in sequence. And then you'll see this kind of chain here, dense, dropout, activation, flattened. These are all very common for neural nets. So dense feeds output from previous layer to neurons, dropout, randomly selected neurons, and the list goes on and on. But the things that are most common here is you have a convolutional 2D layer, max pooling. Anytime you have that, you also have convolutional layers and pooling layers. And then here's the pickle. So the pickle with model metrics, names in order. So this particular code was built up on 2 previous tutorials. It's in the Python programming tutorials. It's some years old, but it's very helpful because you'll see it. And now I'll show you with the quantum coding for convolutional neural nets that there's some analogies between all of these. So this next one sets up a lot of it as far as you have max pooling. So that you have these 2 convolutional neural nets, right, or layers right there. And then at the end, you need a flattened dense, and then likewise. So this is to get, and I think they were using cat dogs for images, but all of this is heading towards that direction of this is the classical. I'll show you, the quantum version of, you can look through all these terms if you're looking to get up and going. So in specific with this, so the first one they run, they just ran 1 epoch, which is like 1 pass through. And then you can see with the additional epochs, so these are their results, that the accuracy goes up. So this 0.6496 to 0.74 to 0.78, which is typical. Now, if you're running more epochs, so more time, so I'm just taking a look at the last one. So you can see the accuracy is already up to 0.83, 0.84, and then you have a 0.8537 with that. And again, so these are downloadable. If you want to really get into the program, you have to go through the tutorials, both in Python, Jupyter notebooks, watch a lot of people code. A lot of times they'll say, you do this, and then you type it into your own, and that's how you learn. Now, here's the quantum approach. So this is Penny Lane. And as far as I could tell, this is pretty good to follow. I did have to do these pip installs, Penny Lane and TensorFlow to begin with. But here's some of the differences. So this is setting up a quantum convolutional neural net. So you'll have Penny Lane as your QML, and you'll keep seeing Penny Lane. And then, they're calling things different. So quanvolution. Actually, I'll show you where I kind of got tripped up on code with this specific one. QML device, default qubit. So obviously we're talking about qubits. We're not talking about conventional. And then QML.QNode. That's something specific for Penny Lane quantum programming. And then you'll see a QML.xval, and then polyz. That's a gate. So that's different. So they say it's very similar, but there is a fair number, and you want to find a bunch of templates to follow, if you're looking to code on your own. And then here's their quant that they're calling, and then their Q results in their circuits. So this is as far as I got. So basically with the code, so you see Q train. So this is training. So Q train. And then you also see testing in here as well. So Q test images. And it's from another paper too. I'm going to put that in when I get everything all wrapped up. But you have to follow these tutorials. So where I stopped is basically when they say the hybrid quantum classical, conversion. So they were able to display these images. I got this error. So basically it's a directory error I need to fix, and it doesn't seem like it's going to be hard to. Now, in Qiskit, it's a little bit different. So they call these things neural network, no spaces, estimator, QNN, no spaces, and sampler, QNN. And the important thing to notice in this is there's certain things that it's an abstract class of QNNs inherit from, and they're stateless, so they can't actually train or store values for weights. So this is for chemical computer devices entering into this world of QML and especially QNNs and QCNNs, and figuring out the best way to go about this. But on the fundamental basis of this, you have unitary functions. The issues with quantum is you can't actually clone data like you can conventionally. And then you also have these a different type of cost function. So this you could call it ULJ, and then the C, they're just different in the quantum realm. So I've seen neural nets where you start off more with a big a classical convolutional neural net, and then you go to a smaller QVC. And I've seen other papers where they start more with quantum, and then you're going into classical. It just depends on what you're trying to do, the limitations of the hardware. But basically, in all these, when you get more qubits, or I should say bigger models that have more qubits, such as 4, it tends to be slower, but your outcome tends to be close, your accuracy tends to be higher. And that's the whole thing with all of these is, finding that sweet spot, and especially, with technologies such as ion trap and gate-based superconducting qubit, which of these is going to be, good for, say, an MVP in Q3 of this year. And, looking at bigger, if quantum is working as it should be, as it's getting better and emerging to that point, not only some papers say that you actually don't need as much training data. And then, other papers also say that, getting larger models, and the larger models is based on, more and more qubits being connected, exponential, processing power, where you can't even get close. So once you get above 50 qubits or quantum bits. So I focused on the Shor's algorithm last week, and in specific, this polynomial time quantum algorithm. Now, if you weren't able to catch last week's, the advantage with this is the math favors the blue line. So they say for 230 digits, you can see the exponential amount of operations that are required in the classical realm. And we're talking about decryption and encryption in these cases. But with the quantum, it doesn't go up nearly as much. So, it's relatively flat, which is good and bad, because, to protect data, with higher security, if there's an algorithm that figures it out on a quantum computer, then it's not as hard. So this is where we left off last week. So this is a part of Shor's algorithm to help find the prime factors of an integer. So this is easily run on Qiskit. So this multi-7x13 mod 15. And the results are this, is basically the primary probability is the 727. And you can see that there's others like that. So I asked the question to myself, what if you continue this entanglement between this Q0 and Q3, i.e. the first and fourth qubits, what would happen? So the 727 turned into this 775 by adding an additional CNOT gate. So the code for that in OpenChasm is this. So you get the QReg, Q3, QReg, Q0. So, it seems like that was a beneficial thing. And I'll continue this because I've got a couple other experiments that I ran after this. and that it could be just noise. And it was run a week after, so you get this gain of 48 shots. So in quantum, it's probabilistic, it's not deterministic. And then some of the other experiments would, show that or suggest that it doesn't look like it's just a random deviation from, experiment to experiment by adding another CNOT gate. So when I added a second additional CNOT gate, it actually switched the primary probability. And I think this has more to do with phasing. So there's, the block sphere representation of this all, but there's something that inherently changed, adding an additional CNOT gate following their pattern. So their pattern was down, up, and then, this is another up and then another down. So from the 644, I saw a similar bump. So as far as this primary probability, it stayed the same, or appears to stay the same, and then increased in amplitude, just like how I added the first one. So adding the first CNOT gate and the third CNOT gate both tended to increase this probability, this amplitude. So basically, I kind of went through all of it, but it has to do with phasing, what a CNOT gate does. And I'll have these slides up afterwards if you want to take a look. And then, feedback is appreciated as well with this too. So the CNOT gate is 2-qubit operation, where the first qubit is usually referred to as the control qubit. So this is where like one looks like a little pin, and then one looks like a bigger cross. And then when this is in the quantum realm, so you have to know all this stuff and memorize all this stuff. So when control qubit is in the this one state, the CNOT gate leaves the control qubit unchanged, performs a poly X gate, and then when the control qubit is in the initial state, you can see it on the block sphere. So this is what's going on, and I believe that's what's reflected in the results. Now, getting into FDA, I stumbled across this very interesting article, and it states the primary things that it states, and you can read through these too, is basically you have the corporate atmosphere is to get the best possible performance, but FDA's concern is more about the safety and efficacy. So obviously, when you have new technologies like quantum, that's going to be very well explored by many big companies out there, and it's more to get your best chance of a 510K, which is the most common submission type and approval type. It is, to do reports, detail input data, model performance. They want to get an idea over time of your algorithm, how it's behaving. And, there's different things. So using data that was acquired with non-clinical protocols that are too different from the device's intended use, and not being aware of bias in all of this. Certain age groups are underrepresented. And actually, there's issues now with CPUs and GPUs. Should inference be possible without a GPU? So that just goes to show, it's just like, what would that be the case? When would your algorithm be run with it doesn't have both CPU, GPU, those types of things? But these things exist. And the authors of this paper, actually, they offer consulting, and they say there's many things that aren't spelled out. And I've looked through most of the FDA AI ML papers, and that's what they say is there's still a lot you have to learn that's in person that's not documented. And how big of a model do we need? What are the best hyperparameters? This is the epochs, so I mentioned that. How many should we train on? And then getting into five-fold cross validations, you're resulting 5 models, So figure safety first, probably for the patient. And then at that same time, it's, you're dealing with this emerging technology that has, great potential, especially as the noise is decreased in quantum bits, and, quantum bits increases as well. Now, this is the PRISMA study that I did. So there's 521 total FDA approvals, they're AI, ML, medical device approvals since the beginning of AI and ML for FDA. Now, in recent years, it's more deep learning, which is more like a deep learning is like a deep convolutional neural net. Pretty standard these days. I removed 115 that weren't as related. That leaves 406. And then of these, removed 215 that weren't brain, head, or skull. That left me, actually it removed 176, and then it left me of 15 reconstruction algorithms. Now, this table here, you'll see the names. These are reconstruction algorithms. They're all huge companies, very well known. And, when I went through this, the other thing that stands out is only one of them for a reconstruction algorithm is for MRI. So the rest are CT. So CT is computed tomography. And I don't know if there was previous, I don't know what the issue is with it being primarily CT for reconstruction, but we could have discussion on that later. Now, one of them I chose here is this GE Healthcare. It's deep learning image reconstruction, and this was July of 2022. Now, the last report was October 2022, so I think this is actually one of the most recent, if it's not the most recent, of approvals. And they said they did a great job in training with thousands of low noise, filtered black projection images. Now, the FBP is this image on the left, and that's going to be the clear of the two. So the two other ones, the middle and the right one, are both GE algorithms. So they're claiming that the right one is just so much easier to use. I don't know. It seems like, I don't know. It's a balance between detail and removing artifacts, basically. But they say this one on the right is their true fidelity image. It's preferred in industry. And then the paper that stands out with this it's a Seth Lloyd paper in MIT, and they say exponential speed up over classical counterparts when data is input as a quantum state. So if you remember seeing this, if you've attended any other quantum talk that's gone over there's CC, which is classical data, classical algorithm, CQ, QC, and QQ. So right now we don't have exponential quantum data to go into that. So, it just depends. So the more quantum that you're off with data and algorithms, the better chance you have for advantage. So the next one is another GE, but this is the only MRI DL that the PRISMA study yielded, and for reconstruction. And they say it works with 1.5 and 3. And I don't believe 7. I don't know if that's for live patients. That's kind of a high field. But basically say more than 2 million patients in the world, shifting the balance between image quality and scan time. Up to 50% exam time reduction. So there was a fair number literature. Now, a lot of this is not found in the FDA approvals. So I had to find this, in their literature that they post in the public. And they say it covers close to 90% of all clinical MR sequences. So you can see kind of like a standard. So 12 international peer-reviewed scientific journal publications have mentioned this. Now, in the quantum realm, for benefit, we're talking about ion trap technology with IonQ, and today's, neural networks and deep learning, you're talking about fully connected neural networks. Now, the IonQ or Quantinuum is one of the few, if not the only, type of quantum hardware that can do a similar things that classical networks can, but it's a higher threshold as the qubits go higher with more entanglement that you can't quite reach. And that also, I'll touch on this, is there are certain cases that you don't need as much training data for quantum, and I will focus on that too. So there's also the NVIDIA's CODA and Q quantum, so CPU, GPU, QPU processing. Simulator benefits. Many people discount it, but that's the primary way that people are getting good results in papers these days. Some of the later papers I'm going to show are still using quantum simulators, and even Dell, Dell is using IonQ's simulators, or emulators they call, but it's noise free, it's limited in qubits, it's really slow, but it's an option. So the second Prisma study here is basically for segmentation. So it's a similar type of study that was done, except for in this case, of the 191, 164 were removed that weren't segmentation algorithm, leaving 27. So significantly more segmentation algorithms out of these 521. And these go back to, late 90s, but more recently in the past, 4 or 5 years, more and more AI, ML, and then more deep learning, especially 2017 and more recent years too. So here's the Prisma study for this, and you can see that the companies I haven't seen too much of. Fujifilm, there is so Siemens Healthcare, but segmentation is basically further down. So reconstruction, which is the one I previously covered, that more has to do with getting raw data. So raw data, and then turning that into images, and it can do denoising, it can do motion, all this kind of stuff. So segmentation is more associated further down medical image processing, and you can see here automatic labeling, visualization, volumetric quantification of segmentable. So that's typically how that one works. Is basically it's huge in demand as well, and deep learning has reached this as well. So the first one I'm going to cover here, so June 17th. So this is basically right before the FDA updated to 521, and there's still many in the pipeline. But as far as the new emerging tech and how long it will take to get quantum approval and IEC and ISO, it's going to take some time, especially for reconstruction segmentation. Now, other things for FDA like classification, prediction, I don't believe that it's necessary to go through the FDA process, just because I haven't found those types of benefits, say binary classification, quaternary classification, those types of things. So these are more fundamental to reconstruction. Is 100% that your image looks a certain way because of the reconstruction algorithm. And similarly with segmentation, it's tied in with other aspects that are more kind of fundamental. So this therapy anesthesia, they said up to 90% of time saved in contour. Now, contouring is a synonym for segmenting. So you're dealing with images. And also benefits generation of pseudo CT from MR images, 100K patients treated on this. Now, there's actually a couple papers out there with brain segmentation and quantum inspired, meaning it's hybrid. So, basically these hybrid approaches, using some aspect of quantum with that, but they're already on a multiple. So this first A, so 2A, they found that it topped their previous KISS net with this, quantum inspired neural net. And then this other one, quantum inspired Firefly algorithm, they said it creates good, that's hippocampus, HPC segments. And these papers are fairly recent, 2022, 2021, to start incorporating quantum into things. Now, the second one is Siemens Healthcare, and basically a lot of these are automatic segmentation. If they're not, like say if it's like many modals, if you can do PET CT and MRI and all these types, then you start to get into, in the recent approvals, you start to get into the more, basically it's not automatic. So it's just, manual or partially automatic is what they call it. So in this case, so algorithm detects brain volume reduction, new algorithms released to users on demand. And then the prospective quantum upgrades for this is, I've kind of alluded to this, but these are really important. So there's a number of papers to run larger data sets on hybrid quantum neural nets. So this goes even back to Nature Physics in 2019. And then there's another paper in 2022. And IBM also in 2022. And that's kind of been known, that would be the sweet spot, especially as error decreases and qubits increase with this. And then also, here's the other thing that people don't know too much about, that in certain cases, you can run smaller training data sets. And it's just like with anything, there's, quantum advantage in certain aspects with this. And then also, forming partnerships. So there's IBM and Cleveland Clinic. There's, Sandbox AQ, and then Mount Sinai. So Sandbox AQ just got a lot of money. So $500 million. So $500 million. And basically they can run these, quantum algorithms on classical computers. And then NYU Langone is more MRI analysis with Fermilab. So there's a fair amount of, interest in this and quantum and seeing all this happen. So I created these 7 principles, and this is based on my original Prisma study of the 521 down to the 191. The one I haven't covered is this principle 3, reduced MRI size while maintaining adequate performance. And this is talking about having, sensors, on tips of probes with, quantum diamond sensors that you might not need, nearly as big a field. There's a lot of cool kind of research with that. Bosch does that research in here. And then QST, which is Japanese focus, they do that too. Multimodal imaging, I'm going to touch a little bit on XAI as well. Now here's the regulatory, impact with all of this. So these are the last 10 that got approved by FDA. So there's a mix. They're not just all, brain MRI, brain CT, is that you'll see, so for enclosures, you're going to have NEMA, you have IEC and ISO, which is going to be the main 2, I believe, for, a lot of the quantum hardware, software. You may also see some ASTM, ANSI, for these. CFR is more of government code, or it's like saying, oh, okay, this is a CT, equipment that does emit X-rays, that kind of stuff. And obviously this has huge potential for breakthrough. So you can just track this, going into medical, if we had 2 last week with Google and Quantinuum. Basically, Google says we have less error with higher qubits, which is, unusual, but, they've had other good, quantum supremacy, and they've had good QML updates with that quantum machine learning. And then you also have, Quantinuum increasing quantum volume. So it's 2 to the 15, which would be 30,000 something, I believe. So I think that means with 15 qubits that, they're getting this high quantum volume. So these are all the gates, so looking to start up with, Qiskit. So this is available to you. And I would go over, you really want to understand theory and you want to understand code. So the theory, supports what should happen in results, based on these matrices. So you have a normal matrix that would output the same thing as the input, like identity. It's look at these as alterations to that, especially with the poly-X and C0, where it's literally just flipping 2 columns. Now, getting into this with an MVP, there's many different things to do. And, say, for instance, on Qiskit, it's easy to flip gates around, but they don't let you alter OpenChasm, which is the code. But then you can switch to a Jupyter notebook and do, Python. But, lots of opportunities. And qubits are rich in information. So a single qubit, you can actually do encoding. And I believe they actually did classification on this specific one, just taking advantage of all the different complex numbers and the phasing and that kind of stuff. Now, Kubo has this thing called Kubo feature selection. So this is similar to the Siemens, paper, or it was a webinar from earlier this week. And it's an option too, right? So typically binary classification mean you can only tell two things, and getting up there, you might need that, quantum neural net or the convolutional neural net. And then this one is more like just replacing a CNN or convolutional neural net, with something more quantum. Now, they say with this scalable quantum convolutional neural net -3D is that you can actually, start off with more data. So I think they started off with 30 by 30 by 30 voxels, which is a 3D image. And then they said that's the key. And they say also it's not using as many qubits up front. So just to get better results, it's like, a perfect solution. They also have just the regular 2D version, which is without the 3D at the end. These are perfect solutions for, noisy quantum computers. Now, the other thing they said is with this RF train is that, it also helped to improve results. And you can couple these. So there's many other types of papers out there that run on traditional, it's called POVMs. And then this one at the bottom with a PVM, for instance. So these are the parameters that they use. So again, 32, 32, 32. And most of the images I see are like 26 by 26 in 2D. So it's worth taking a look into with these papers as far as, how much you can get out of today's noisy hardware, using different techniques and neural networks. And then this last one is about XAI, explainable AI. So it's basically saying neurologists come first. Developers need to keep going back to neurologists. Neurologists need to have as many of the big explainable steps understood instead of just relying on an answer, without too much information behind that. And then, there's these papers. So it's actually in the quantum world, it's a pretty well studied area, explainable AI, and Shapley values, ridge functions, and basically, I like how it says, transfer and adapt the well-established concept of Shapley values to the quantum realm. So I think that was, pretty straight out of the paper. And then, this IBM Amgen paper was kind of ahead of its time, and they use quantum support vector machines, with explainable AI. Most of the papers that do awesome stuff like this will wind up saying, we wish we just had a better quantum computer. And this is more XAI information, and it's still a developing field in regular deep learning. So, but there could be breakthroughs, so you could have something open up on quantum and, additional hybridness. And this is where the startup is right now, is focusing on a classification software as medical device for brain disorder. This would be Q3 this year, an MVP. So that's why I'm going into the, QCNNs and quantum neural networks and, learning from all these things. This supports that. And then this is accelerator reconstruction. So, basically I showed you the, dozen or so reconstruction algorithms that have got approval. So when will the next quantum upgrade be? Will they only allow quantum simulator? Will it have some mix of ion trap technology? Will it only be ion trap or, gate-based, these types of things? But figure the FDA is more considered about patient safety. So by the time IEC and ISO would approve this, in order for the FDA, it would, the technology, is going to settle down by that point. And then here's all of the myriad options of machine learning and, neuroimaging, neuroradiology. There's many different approaches. So with all this, I want to give this chance to any questions, comments, and then I'll open things up. And then you should be able to come on, unmute. We have a bunch of, everybody's returning, which is awesome. So Austin or Tim, you can go ahead.
Well, one thing I've been working on is the IBM Quantum on their cloud. So that actually works really well for Qiskit. I was just going to mention that. And for their programming, they've got, I forgot the name of it, but it's very similar to Jupyter Notebook. So it's also a good option I would recommend, and it's free. So you can write the programs, and then you can even graphically like move certain icons to actually create a circuit, and then run that quantum circuit, and then it's all free.
Yeah, every time I go on, it just keeps giving me more runs. So it always says 5. I always have 5 more. I don't know what the cutoff is with qubits. I always run on Nairobi, and it's 7 qubits. Now keep in mind, that's only like 32 quantum volume. And then, Quantinuum is saying that they got like 30 something thousand, 30K
Oh wow.
with quantum volume. So I think when they publish all that, what they're saying is that it's relatively under control for, again, they say 2 to the 15. I'm assuming that means that it's for 15 qubit systems. That, anyways, that specific report, they said that they basically it's 3 times faster to run a quantum experiment on a quantum volume that's higher because it doesn't have as much error. And it has a couple more qubits too, I think. But all of those, the forecasts with ion trap it's not huge qubits. I think 2026, 2028, we're still looking at 1,000, and I don't think too much more than that. So it's all about the specific applications, such as medical imaging for radiology. It seems to be fit pretty well for that. And they actually, one of the hardware manufacturers say that they do QCNNs and they work well. So
Okay. And then you haven't noticed it seems like Qiskit is used more often than Penny Lane. Now, is Penny Lane like better, like specifically for data science?
well, it's known for QML, so not everything is
Okay.
QML, and then kind of QCNNs follow under that.
Okay.
And Qiskit just has, without knowing too much about it, they've run over 2 trillion quantum, circuits on systems, and I would assuming mostly on simulators. But yeah, they just have the infrastructure, and like it said, like I can import and I can install Penny Lane on Qiskit and Jupyter just fine, I believe. And then I like with one of these circuits, I was having an issue with a directory. And actually, the best tutorial for QCNN I found was through Penny Lane. And it doesn't look like it's a hard fix. It's just, it's just one of those things. Because I got to a step and I pushed enter and it was chugging. And then it was like, I didn't get my images. I was supposed to get like, a block of MNIST images comparing them to each other. So, but yeah, I think a lot of it's meant to be open source, free. Like I mentioned before with Jupyter Notebook, the reason why it's on the web is, because you can get HTML and other service updates free, because it's web-based. It literally opens into a Chrome browser tab. Awesome. Anybody we haven't heard from? So Ron or Hannah? And then if not, we have so George or Austin?
Yeah, I've got a quick question. What is Prisma?
A Prisma diagram is basically, if you look at all these academic papers, and if most data isn't structured, so you start off with like, say, thousands, and in this case it's 521, and then you go through, screening, and then you're left with what you want. And sometimes, you say, for instance, in mine, there was like oral and all different types of medical issues, and then in a lot of times, like in Google searches and stuff, you'll get duplicates, so you'll remove duplicates as well. So it's like a thorough way of getting to what you want, and you set a criteria. So say, for instance, if you want to set it to like a certain type of algorithm, so anything else that isn't that by that point, but it's meant to also be efficient. So I've seen Prisma used, just to get rid of, like I said, a lot of duplicates up front. Like, so it's so your eyes don't even see things that aren't interested in your study.
Thank you. So it's a intelligent document search.
Well, yeah. I mean, I'm sure AI has been applied with it, but a lot of times you'll say if an article contains the word qubit, quantum, this or that, you can include, and then you can also exclude. So if it does contain any of these words, we're not considering it. So it's usually, in a lot of papers, especially reviews, it's usually the first image that you see, and it's not necessarily always the prettiest, compared to other kind of more graphical things. But again, I think the biggest thing is just to narrow down from like this vast amount of information, include or exclude.
Okay, thank you.
So I would see it a lot with, say, multimodal. Probably the same thing with the XAI, explainable AI. So it just depends on what you want to get out of it. And then anybody we haven't heard from? Go ahead, Ron.
Hey, I've always been wondering, you report on a lot of these FDA approvals for various ML, AI and ML things. Are you getting some sort of sense of what sort of budget is required to get an approval?
Well, the best sense was the paper before all of the Prisma studies, and they said in specific, like it's that whole trying to get performance, but in reality, you really have to research and find out what would make the most safe product for the patient. So that's like the whole FDA, their main thing, right? Now, performance increases over time. New technologies going from like an ML to DL, and yeah, it's just you usually can find that kind of stuff, but as far as like an exact budget for, saying for a new reconstruction, quantum-based, those types of things, I don't think that's going to be out there for that. There's, again, the paper I've been talking about, this article, there are two consultants, and I think one of them is an MD, and then it's a complex thing. So for sure, you want to understand precedents, what have been the issues with previous algorithms. You have to have a predicate device going into it. One of them I looked at, one of these, the segmenters, it was like 3 or 4 different types of predicate device, standard devices, and reference devices, what they had. And I don't usually see that's the case where you're saying ours is going to be so much more accurate. It's usually the case saying ours is as good or better. But it's predicate devices are usually that case. Like over the course of their 3 or 4 years of being on the market. And, we think ours will, do a similar type of thing. But lots of reports,
Yeah, but I'm more trying to focus on the process of getting the approval. Is this, are you submitting stuff directly to the FDA? Are they using third-party entities to certify your work? That sort of thing.
Yeah, there's a thing called algorithm change protocol. So, and specifically it's for like the deep learning algorithms that they will change over time. So that's part of it. And like I said, like I've reviewed, there's 4 or 5, let's say 3 or 4 of the key documents, and I've done text to speech and, gone through. I don't understand everything to it, but it's just one of those things where it's some of it is in text, and like these other consultants say, some of them you do have to talk to the FDA. So.
Good. All right. Well, I can give you an example of having to deal with the Center for Medicare Services. It's been about 10 years now. 10 years ago, they passed a law that required medical charting systems to get certified for something they were calling meaningful use. Okay, so the process for that was what CMS did, the Center for Medicare Services did, was found a bunch of third-party companies that are in the business of reviewing certifications, not just for them, but like, ISO 9000. These companies do all kinds of certifications. At the time, Medicare put a thing on their website that said, we don't think it's going to be a hardship for software vendors to get these certifications. It should only cost about $1.5 million. So immediately they basically crushed all but the biggest companies as far as having the ability to get the meaningful use certification. And then of course the best part is you got to do it every 2 years.
Yeah.
And when I first looked into it, I got in contact with one of the third-party certification entities, and just to get in their queue was $20,000.
Yeah, I'm sure that.
So what I'm wondering is, have you had any experience with the FDA as far as, is there something similar that has to be done, and what sort of budget do you need to get something approved?
A lot of this falls under, they say you have to be an excellent organizational practice, and I'm sure that implies financial.
Yeah.
And they have this good machine learning practice. I think it's either GMLP or one other letter in there, and their guidelines with all these too. But it's basically they call it organizational excellence. Do you meet organizational excellence? And I think that's probably tied up in a lot of the financials. So there's more to that, and I've done other kind of studies on that. But yeah, figure it's both, because if you get started with an algorithm and it's not all in-person verbal communication, because you have to know all of the regulations, and kind of how I presented here is the 2 consultants said that bias, sometimes would your algorithm run just fine on limited hardware, without a GPU. So I think the biggest thing is talking to other organizations that have gotten approval in specific, the people that were working on that specific algorithm or software, those types of things. Anybody else we haven't heard from? Austin or Hannah or Tim, you can go ahead.
Nothing really to add, but just happy to be back and getting back in the rhythm of these meetings. Sorry I've been gone for so long.
Oh yeah. Yeah, it's good to have you back on. They should be at 3. I had to change things around to wake up earlier in the morning and not stay up at late as night. So it'll probably be 3 for, unless something awesome happens. And then anybody else? So I talked about, the medical we've talked about for sure. We talked about Jupyter Notebook, convolutional neural nets, quantum convolutional neural nets, and the Siemens. So the Siemens is basically Kubo. So Kubo is just binary optimization, and or it's at least quantum annealing. And a lot of these studies that you'll see are just with numbers and these types of things. But if they're healthcare companies that are doing the studies on MNIST or whatever data set, figure that they're looking at other things. And even the StrangeWorks Deloitte paper, they said, I think it was 26 by 26 images. I believe, for medical images, you have to get up to, it's like 256 by 256. Although for MRIs, a voxel 60/60, I think 60/60/30 is that. In this particular one, I believe they're doing 30/30/30 on this paper that I went over. So yeah, the higher arching thing is, yes, the quantum computers have to work better, but the ones, especially these scalable quantum convolutional neural nets, 2D or 3D, seem to be going about it a little different way, so you don't need as many qubits and you get better performance. And these are all running on quantum simulators. They're not up to hardware yet. Go ahead, Tim.
Yeah, I was just going to mention that I'm joining this startup that uses multi-omics data to help with cardiac issues. And they're still trying to figure things out, how they're going to proceed with it. But I'm thinking in the short term, we'll use classical computers for the machine learning, because then we can start to get some immediate results. But try to push that into quantum machine learning, because eventually, probably, the quantum machine learning will be more efficient.
Yeah, and I would look into annealing too, for sure. Most of, if not all, so Polaris QB, Metin AI, Johnson & Johnson, which is Janssen Pharmaceuticals, they all use annealing. Now, the Siemens Healthcare one used annealing, and it's pretty much the industry's go-to if you want good results. It gets the qubits up, but it's it's limited in functionality to optimization. I think one other thing it can do, but yeah, you definitely want to check that out. And there's things, the IonQ Dell simulator, I don't think it's using real hardware yet, but there a lot of these papers in academia, they're getting good results, a bump, using quantum simulator for one part and then classical for the other. So taking advantage of what it can do limitedly now. And if you're doing like multimodal data, that kind of stuff, and Ron would know this probably better than I would, is you have GPUs too. So you still have that hybrid, and what specific, package would be good to use, CPU, GPU, and then especially as, the QPUs come in, so.
Okay.
Yeah, again, you always want to make sure you understand the distinction that a simulators, wherever you run into them, are classical machines. We've heard about Penny Lane having a really large one available, like 30 bits or something like that. But that's all classical stuff. When you're actually running when you're actually running your algorithm on real quantum hardware, what they refer to that to is you're selecting a different back end instead of a simulator. You're selecting actual hardware. And we also heard about D-Wave and its annealer. Annealers are big in quantum machine learning due to the fact that a lot of the algorithms that are going on in quantum machine learning are centered around improving performance in various ways by trying to actually solve the equations, or at least a subset of the equations for like the back propagation or the forward propagation. And you know, so they're trying. These are optimization algorithms, and the quantum annealer hardware has got a kind of a built-in benefit to do things like the QVC and searching for quantum eigenvalues and stuff. That's the thing that they're relying on. So I had a question for Tim. You said that you were looking at some sort of data set for cardiology. Is that, do you know where the source of the data is? Is it like imaging or is it like EKG?
I don't know yet. I haven't really started working for that startup. So I still got to talk to them.
Sounds
Yeah,
interesting.
I mean, go ahead, Ron.
That's all I got.
There's been some paper on EEG. There's been quantum sensing papers on ECG or EKG. And, you know, like with anything, the devil's in the details. Like the quantum annealing stuff, there's linear, there's nonlinear systems, like that the Siemens slides today. And, you know, the more you know about the specifics, the more it helps, you know, because it's like with anything, like it's hard to learn Python, and there's a lot in the background. And say if you want to incorporate Keras, you know, what's the other one? So there's different packages that go into it that they themselves do things too. So, but with anything, if and this goes for everybody that wants to code in Python, and I think this has come up before, definitely take a tutorial in jupyternotebook, do a tutorial videos in Python. For me, where I am right now with Python, it's still like, you know, there's so much terminology that you keep having to think. Another thing that helps is when you get an error, just copy and paste that error straight into Chrome. And then 9 times out of 10, you'll get that direct answer right back. So just don't give up. Because you know, same person's using this Penny Lane, you know, QCNN code, and they get the same error that I'm getting. It says you need a directory, but then when I go to, it doesn't have what goes in front of that to put in. So then that's probably a new section on its own. But if you want to do quick wins, and it's really important to run no matter what field you're in, do the KISS kit. You can go through Shores, Deutsche Jose, Grovers, all those, and it's just one click and then one more click, and it's literally running. And they're quicker these days. So the one I ran, these 3 I ran this week, it was like in the seconds. I didn't even have to wait like 45 minutes. It was like 25 seconds to queue up and all this stuff, 6 seconds to actually run. Now they did change it to, and it seems like the results have gotten better because it says 6 seconds and hybrid quantum classical workload, and more fine print. So, but it's really important to run because then, you know, you have to run, you have to do tutorials, all these types of things. So awesome. So any other last questions or comments? Anybody we haven't heard from?
Also, this is for Tim. The code editor inside the IBM Quantum Experience is absolutely Jupyter Notebook. And when you can start it up, you can actually select the Python kernel that you want. I assume that if anybody in here is writing Python, they've already started. If you're looking for a tutor for Python, I did teach a short CE class at a local community college here in Chicago area on writing Python for makers, like running Python on a Raspberry Pi. I'm available if you want one-on-one, or if you guys want to have somebody that you can bounce ideas off of.
Okay, I'll
Also,
keep that in mind.
I'm also a tutor for Bash scripting. I've been doing that for decades. So
Okay.
Appreciate that. The other thing is there's other ones called Jupyter Charm. And then when you're typing, it'll start auto-filling what you should be doing as far as like the next command. And I saw a video on that and it seemed incredibly helpful. So, and then there's Jupyter Lab. So that's a step up from Notebook, but it's, it's heavier, but it has other things, like files and stuff. Like it's a lot more is there, but I don't know, you could do just fine inside the Qiskit Jupyter Notebook, but it has probably the least functionality of what I've mentioned out of those 3 or 4. I would definitely shoot for the YouTube tutorials for sure. There's a gentleman, his name's Mosh, and there's their Python on their website for that QCNN. Somebody will do a video typing in the code and explaining it, and then that's the one that I use for that in Python. But you can't go wrong with videos, because a lot of times they'll tell you just exactly what to type in, even if it's just addition, subtraction, all that kind of stuff. But it's just helpful. Awesome. So any other last questions or comments? Appreciate all the feedback. Good to see everybody on. This has been discussion 72 for Thursday, March 2nd, 2023. APS physics is going on. If you're not going, definitely catch the news on that. Thanks, everybody. Have a good rest of your week. Take care. Bye.
Bye.
thanks, Kevin.
Thanks.